Bismillah ar-Rahman ar-Rahim. Assalamu alaikum. Dear students, this is the starting of lecture number 2, magnetic circuits, and I will be solving few numericals so that it might help you. So first of all, we will be solving numericals from our textbook, and then we will be solving from another Chapman book. So the first example states that we have a magnetic circuit of a primitive relay, and this is a kind of relay. What happens is that there is a coil here. This is the coil here. There is a coil here, and when the electric current passes through this coil becomes a magnet, and this part actually connects with the coil. This is a typical example of a relay, and the coil will connect like this. So if you want to make a circuit, and when we de-energize it, when there is no current in the coil, this spring will push the coil back. So this is a typical example of electromagnetic coil. So the question arises, this is the application is related to electromagnetics. So the coil has 500 turns. We have n equals to 5. Mean core path length is 360 millimeter. This is the mean path length, the complete length. And air gaps we are assuming are very small. It is 1.5 millimeter each. They have already given us the flux density. And the flux, the amount of flux that should flow, that is actually equals to flux per unit area. So in this coil, the amount of flux in this particular area of cross-section coil, the flux density should be 0.8 Tesla. So this much amount of if flux density exists inside our core, then this part, the plunger, will move and will get attached with the U-shaped part. So the core they have said is cast steel. So in the book they have also given us the B versus H curve for cast steel. This is actually the property of material. It is based on the permeability of the material. So the first question is find the current in the coil. So in simple words, how much current should flow in the coil so that this air gap will finish, this part will get attached with the U-shaped part. How much current do I need? And we know that 0.8 Tesla flux density will cause this I part to get attached with the U part. So we can start our question. First of all, we have been given this 0.8 Tesla. So for 0.8 Tesla, and the material that is given to us is cast steel. So if you look at 0.8 Tesla, here is 0.8 Tesla, and if we go here and we go here, so you can see it is approximately a little larger than 500. So we assume that, okay, so the amount of field intensity that is required in cast steel in our core will be, HC will be 510 ampere turns per meter. So this will be the HC. Okay. Now let's make an equivalent circuit for our core. We can see that we have a source. Then there is a reluctance of the cast steel core. Then we have air gaps. We have two air gaps. We assume that we combine the effect of these two air gaps to one reluctance. So actually the length of one air gap is 1.5 millimeter. For the two air gaps, we can say that it is actually 2 into 1.5 centimeter. We are combining the two air gaps with one reluctance. Now what is the question they are asking? They are saying that the B should be zero point 0.8 Tesla through this coil. So how much, if we know the Ft, we can calculate, we have N, we can calculate I. So if we know Ft, we can calculate I is equals to Ft over N. Now how to calculate Ft? Ft is basically composed of two parts. One is the part that is being dropped, that is the force that is making 0.8 Tesla of magnetic flux through this core. That is the core which we call Fc. And then there will also be a core that will causing there will also be a force that will result in forcing the flux to flow through the air gap, and that we call Fg. So these will be the two forces that will be actually causing the flux to flow in this core. So if we can calculate these two forces, we can calculate the total force, magnetomotive force, and then we can calculate the current. So to calculate Fc, we have a very common formula. We know H equals to magnetic field intensity equals to, and we know this is actually F. So the formula will become Fc equals to Hc and Lc. And for the cast steel iron, we know that Hc is 510. How do we know that? It is against 0.8 Tesla of flux density. We take it from this curve. So this will become 510 into 0.36, and this becomes 184 ampere turns. So from where did the 0.36 came? 0.36 is actually the LC of the core is actually 360 millimeters. That becomes 0.36 meters. So this is the calculation of the force, magnetomotive force that will cause the flux to flow through the core. Now we have air gap also. To calculate for the air gap, let's look Fg. What will be equals to Hg over L of G. L of G, I have said that we are combining the two together. So L of G, we can say it is 3 centimeters, and we will convert it into meters. Now how to get magnetic field intensity, that is Hg, for the air gap? So this comes from our formula. We know that Bg equals to mu G. Now let's go to the simple formula. B equals to mu H, and for air gap this will be actually mu naught, because relative permeability is equals to 1, and it is Hg. So we can write Hg equals to Bg over mu naught. So this equation will become Bg over mu naught into we have the length Lg, that is the length of the gap. G is for gap. We have combined it together, so this will become 2 into 1.5 centimeters, and we will convert this centimeter into meter by multiplying it with 10 to the power minus 2. So yes, student, it will become like this, and the Bg, and this is the value of the flux density. Now there is this assumption, as it has not mentioned the fringing effect. So what we are assuming is that there is no increase in the there is no increase in the cross-sectional area, and so the flux density that is passing through the core is actually equal to the flux density that will be passing through the air gap. So by this assumption, we can say that it is 0.8 as it was in the core, and mu naught we know that it is 4 pi into 10 raised to power minus 7. So the value for f of g will be then become fg equals to, and we multiply this and it will become 19100 ampere turns. In the students, there is a mistake that I have done. It is actually millimeter, 1.5 millimeter. It is actually -3. So we convert millimeter to our meters, and that is why I multiply 10 raised to -3, and the value of this will become 1910 ampere turns. So you should have a very clear concept. What is this value that I am talking about? This is, so let's make it a little more comprehensible for you. So what I am trying to say is, there was a certain amount of force. This was the reluctance of the core. This was the reluctance of the air gap, and the force should move flux through these two areas. For moving from the reluctance of the core, how much force was required, that we calculated. We knew the magnetic field intensity, we knew the cross-sectional area. This was 184 ampere turns. But to move the same amount of flux density, same amount of flux through the same amount of area of cross-section, the amount of force that is required over the air gap, because it has a very high reluctance, the amount of force that will be required is 1910 amperes turn. So the total force that we need to apply in our system, total force that is required is Ft, that will be equals to Fc plus Fg, this value and this value, and this amount equals to 2094 ampere turns. 2094 ampere turns. Now the original question, if you go back to the question, find the current in the coil. So to produce this much force, magnetomotive force in our whole circuit, how much current is required? That we can easily calculate. We know F equals to Ni. So I is equals to Ft divided by N, that is 2.294 divided by 500, and the total current that will be we need, that is the answer of our question, is 4.19 amps. So this is how we will calculate the first part. Second part, it states that compute the values of permeability, and relative permeability of the core. So if you want to calculate the value of permeability of the core, we know from that formula, the basic formula we know, BC equals to mu C of HC. So what is the value of BC we have given? We have also calculated, if any value you will take in the linear region, you can get this value. This is 510. So mu C, the value of the core will be 1.57 into 10 raised to power minus 3. Now the relative permeability's formula is mu R equals to mu C. C is for core divided by mu naught. So we have 1.57 into 10 raised to the power minus 3 divided by 4 pi into 10 raised to the power minus 7. And the relative permeability of our core is, this will be 1250. And this relative permeability means that our cast steel core is 1250 times more magnetic as compared to the air. So this was our part B. And for the part C, let's see what's the part C. If the air gap is 0, now in the part C it states, if the air gap is 0, find the current in the coil for the same flux density. Now, if it assumes that this is 0 millimeter, so what will be our magnetic circuit? Because this, it has stated 0. This is finished. Down there is no air gap. So this will be reluctance of core. This is reluctance of gap equals to 0. We have a short circuit here. We have like this. So how much is required how much current is required to maintain a flux density of 0.8 Tesla? This is the question. This should be very simple. All of the force required should drive this flux through the core. So as we have done here previously, we have calculated. I showed you it is equals to this. So a magnetic field intensity is equals to Ni over Lc, that Ni is F. So we can write Fc equals to, in this case, part C, total flux will be actually equals to the only force required to drive flux from this area. So from the graph, we know for B is equals to 0.8, for BC equals to 0.8, we have calculated. Here it is 510. HC was 510 returns per meter. So it will become 184 ampere turns. Actually, it is this value. We have actually calculated this. In this case, when this is 0, it is only asking 184 ampere turns. And I will be then Ft over N, that is 184 ampere turns divided by 500. So only 0.368 amperes. So this means in part C it says if the core is like this, and in part A the core was like this, so the magnetic circuit has two reluctances, one from the core and one from the two air gaps. So I hope this is clear. Thank you. This was an example 1.1.